everyone, I am Amin Sheikhi, currently pursuing a master's degree in mechanical engineering, with my primary research focus on CFD simulations and internal combustion engines. In today's video, we will discuss how to choose the best gird or mesh, determine the number of parcels required for our simulations, and establish a safe range of time steps for our simulations. Converge has an innovative approach to gird generation in which the gird is automatically generated at runtime. To make this automatic gird generation possible, Converge uses a modified cut cell Cartesian gird generation method. This process allows for complex surface intersections to be represented more easily. Three types of most important meshing options in Converge are the base mesh, adaptive mesh refinement or AMR, and fixed embedding. Let's have a look at these options in Converge. Here is our gird control options we usually use, like base mesh, AMR, and fixed embedding. We can use fixed embedding to refine the gird at specific locations in the domain, where a finer resolution is critical to the accuracy of the solution. For example, when simulating sprays, you can add an area of fixed embedding by the nozzle to resolve the complex flow behavior. Fixed embedding allows the rest of the gird to remain coarse to minimize simulation time. In this figure, you can see the fixed embedding near walls and nozzle spray domain. Also, we can use adaptive mesh refinement or AMR to automatically refine the gird based on fluctuating and moving conditions such as temperature or velocity. This feature may be used to obtain a refined gird in flow regions of interest, allowing complex phenomena such as flame propagation or high velocity flow without unnecessarily showing the simulation with a globally refined gird. This figure shows post-processing of a gird generated by AMR for a time involving spray bomb case. In this case, the velocity is allowed to embed 3 levels, while the temperature is allowed to embed only 2 levels, which significantly reduce the computational time as compared to a simulation with fixed embedding or with a finer base mesh size. For each fixed embedding, you must specify an embedding scale that indicates how Converge will refine the gird in that location. Converge scales the embedding gird according to this equation, where base gird is the cell size of the base gird in X, Y, and Z directions. Embedded scale is the scaling factor, and embedded gird is the new gird size in all 3 directions. For example, if we use 2 mm for base gird and use AMR of fixed embedding scale of 3, then we will get 2 divided by 2 to the power of 3 gives 0.25 mm. But the question is, how finer mesh we need in our simulation? In a study that Converge have done about gird sensitivity named Gird Convergent Spray Model for Internal Combustion Engine Computational Fluid Dynamics Simulation, they examined 7 different mesh resolution for a nozzle diameter of 0.14 mm. Cell size and corresponding embedded scales are shown in this table. They started from base gird of 2 mm without embedded scale to embedded scale of 6, which gives 0.03125 mm cell. As shown in this figure, velocity varies significantly as the mesh resolution change for relatively coarse girds. On the other hand, as the cell size is decreased, the gas phase velocity near the nozzle increases, resulting in lower relative velocities and less drag. This figure clearly indicates that convergence in the gas phase velocity is seen for cell size below 0.125 mm. However, it shows that even a cell size of 0.25 mm, which somewhat underpredicts the near nozzle gas phase velocity, is adequate to reasonably predict liquid penetration. At the end, Converge recommends 0.25 mm mesh based on accurate results and efficient computational time. If you use Converge, you will see it wants number of parcels for simulating spray. Converge recommends 1.5 E-10 kg per parcels in range of 0.25 to 0.35 mm grid. Now let me do an example in Excel. We need injection mass, I give it milligram. We need number of nozzles. And finally, we will get number of parcels. Here, for example, if we give 16 mg fuel and 7 nozzles, then we need to divide the fuel mass in the domain to nozzle numbers, multiplied by Converge estimated parcel mass. And because my fuel unit is milligram, I divided it by 1e6 to convert it to kilogram to match with Converge estimation. Now we will get number of parcels per nozzle to use in our simulation. The next step is how to control our time step. Converge requires that we specify some methods of time step control. Very small time steps are numerically stable, but they are computationally expensive. Larger time steps allow Converge to generate a solution more quickly, but larger time steps will reduce accuracy and too large time steps will be unstable. Also, it's proven that the time step in transient simulations work like under relaxation in steady simulations. Converge allows you to specify one of two methods for setting the time step. You can specify a fixed time step or a variable time step that is calculated internally. In second option, Converge performs a number of checks and calculations to determine the size of the next time step and takes the larger time steps that satisfies all of the application limiters like deity of CFL, deity of parcel, and deity of chemical calculations. Now, it is important to control your time step in every stage of your simulation for best results and computational time. Converge automatic time step depends on gird size and engine or spray speed. I usually check the time step to stay below 0.01 cat when injection and combustion is happening, and I set minimum deity to time step like 0.008 degree cat in simulations. The important fact is the engine speed is not same in every simulations. Because of that, I convert my maximum time step in crank angle degree to seconds for using in Converge. This is how I do. We know that d theta divided by DAT is equal to 6 times the engine speed. Here we know that T is in seconds, theta is crank angle, and N is engine speed in RPM. For example, here we need speed of engine in RPM, time step in degree, and time step in seconds. If engine speed is 2000 RPM and I want at least 0.01 cat time step, for converting in seconds using formula, we will have d theta divided by 6 times the engine speed. Here we will get time step in seconds to use in our simulations. In closure, these values are the best estimations for diesel engine, and they don't guarantees for every ICE simulations, and heavily recommended to do gird and time step sensitivity analysis for every scientific projects. And at the end, here are my references for this video. Thank you very much for sharing your time with me, and have a nice day.